I'm sorry. So I think I'm having issues with internet services this morning because you couldn't see me and I wasn't moving. And then I lost the internet. And normally when I come onto my computer in the morning, it's automatically connected to the internet. It wasn't this morning. But you should be able to see me now, right, Rachel?
Yes, I can see you.
Okay. All right. Okay, let's jump into today now. So the endocrine system, it works in coordination with the nervous system to maintain homeostasis of the body. They work by slightly different means. One works by a combination, the nervous system works by a combination of electrical and chemical means. The endocrine system works specifically through chemical means. The effects of the nervous system are fast, and as long as the stimulus keeps occurring, those effects will continue. So as long as the neuron keeps firing, the action for the response will continue. However, as soon as the neuron quits firing, the response stops immediately. With the endocrine system, you get the hormone being secreted. It circulates around in the blood for a little bit, and if it finally binds to one of its receptors, it will initiate a response. Therefore, it tends to be slower. However, the response is going to continue until the hormone is removed from the body. It breaks down or it's removed completely. Breaks down or you quit producing more. Therefore, the effects are longer lasting and more widespread. So comparison and contrasting of the nervous system and the endocrine system. The nervous system communicates by means of electrical impulses and neurotransmitters. It releases neurotransmitters at synapses at specific target cells. Endocrine system is going to communicate by means of hormones, and it's going to release hormones into the bloodstream for a general distribution throughout the body. It usually has, the nervous system usually has relatively local specific effects. The endocrine system generally has very general widespread effects. The nervous system reacts quickly to stimuli, usually within 1 to 10 milliseconds. Remember, that's 1,000th of a second. Endocrine system tends to react more slowly to stimuli, often taking seconds to days to occur. Nervous system stops quickly when the stimulus stops. The endocrine system may continue responding long after the stimulus stops. The nervous system adapts relatively quickly to continual stimulation. The endocrine system may adapt relatively slowly, but it will respond for days to weeks. And it's just based on the fact that one of them is working through electrical impulses and neurotransmitters. And remember that neurotransmitters, they don't have to diffuse very far. When they act, they're acting right through the synaptic cleft. And if you remember, that synaptic cleft is a matter of how many, was it micrometers? 20 to 40 micrometers. They're very, very small. The endocrine system in response is going to secrete that hormone, which is going to circulate in the blood for a couple meters, possibly, until it reaches a target cell where you receive a response. Neurotransmitters, once they're released and diffuse across the cleft, and then you stop secreting them, their effects stop almost instantaneously. The hormones, on the other hand, are going to last for a while. Different organs involved in the, and I'm sorry, I'm going to have to do something that I thought I'd done already. And it's going to, of course, take me to the very first screen again. Different organs of the endocrine system. Starting at the top, the pineal gland. Remember when we talked about this with regards to the brain, it's going to secrete melatonin, which helps maintain your circadian rhythms. The hypothalamus, the major coordinator of the endocrine system. The pituitary gland, the thyroid gland and the thymus, and the parathyroid gland. The adrenal gland and the pancreas and the gonads. We're going to talk about other things that also other tissues that also secrete hormones. That are considered endocrine organs, even though they're not the major endocrine organs, but because they secrete hormones, they're endocrine. So first question, nervous system reacts to stimuli blank compared to the endocrine system that adapts compared to the, let me start this over. Nervous system reacts to stimuli blank compared to the endocrine system adapts blank compared to the endocrine system. Did I maybe have a typo in here? Let's see. No, I don't have a typo in here. And has effects compared to the endocrine system. What's the first one? What's the first one? Quickly. So nervous system reacts quickly, right? Good job, Kevin. And blank adapts blankly compared to the endocrine system.
Quickly.
It's quickly. It's not going to react slowly. Then remember, the nervous system is going to be quick and longer lasting. And has blank effects compared to what? And Kevin, you can't
Widespread.
Say it again, Zena.
Widespread.
Widespread. So nervous system reacts to stimuli quickly compared to the endocrine system. It adapts quickly compared. that really does look like a typo, doesn't it?
I see what you're saying. It's confusing though.
Yeah,
It took me a minute to figure this one out.
Yeah. And I want to say that the nervous system is more specific. I thought the endocrine system was widespread.
Yes. So it's quickly specific.
Yeah,
all right, let's go with quickly specific. Yes. Even though that's a really badly written question, and that did come from the publisher.
That one was tricky.
Yeah.
Yeah, it's just, yeah, not so easy. You have to read it a few times.
And it's tricky just reading it. Okay. All right. Overview of the endocrine functions. So endocrine system functions in reproduction, metabolism, energy balance, growth and development, body defenses, your immune system, blood making, fluid and electrolyte balance, blood pressure regulation, and much more. Endocrine glands are going to be what are going to produce the hormones. Endocrine glands are ductless, so they secrete their molecular products into the bloodstream without ducts. So just to put this into proper context. And Jade, I understand. So here's a blood vessel.
I'm like, if the whole class would see me right now, I literally look like The Walking Dead. So I'm like, oh.
Oh, that's bad. Okay. Okay. So rather than, and actually we're going to change it a little bit more here. That's an endocrine gland, secreting things into the blood, circulating this way. And so this is an endocrine gland. It's going to secrete its hormones or chemical messengers, aka hormones, immediately into the blood. Exocrine glands, on the other hand, are going to secrete onto a surface via a duct. Exocrine glands. Via a duct onto a surface. Endocrine glands secrete via ductless glands into the blood. Exocrine glands are going to secrete onto a surface via a duct. Hormones only affect target cells or organs that have the receptors that will bind to that specific hormone. If an organ doesn't have a receptor for a specific hormone, that hormone has no effect on that organ. The hormone is going to determine what effect that hormone has by whatever that hormone does once it's activated by the, assuming whatever that receptor does once it's activated by the hormone. So if an organ does not have a receptor for a specific hormone, nothing occurs. Even if that organ is soaking in that hormone. Receptors are going to trigger different things. We may have hormones that have different, that there's different receptors for that specific hormone. Just like we saw with the neurotransmitters. Depending on what occurs once a hormone binds to a receptor, the hormone may stimulate something or eliminate something. It may stimulate something or downregulate something else, depending on whatever that receptor activates. Any questions so far? So endocrine glands are going to secrete substances directly into the bloodstream. Exocrine glands are going to secrete substances into ducts onto epithelial surfaces. Which of the following is true regarding endocrine glands?
B.
B, they secrete their, B is in Bravo.
Yes.
Okay. You're close, but they don't have ducts. Endocrine glands don't have ducts.
Okay.
D is
They're
in dog.
ductless. Say it again.
D is in dog.
D is in dog. That's right. So they secrete their secretions, they release their secretions into the blood. So hormones are defined as chemicals that are released into the blood. A cell, the target cell, are the targets of a hormone that have the receptor for that hormone. The receptor can either be on the cell surface or inside of the cell. If there's no receptor, the cell won't respond. Hormones can do lots of different things. They can stimulate the synthesis of molecules within a cell. They can eliminate the synthesis of molecules within a cell. They can change the plasma membrane permeability of the cell. They can alter by upregulating or downregulating cellular metabolism. They can cause the secretion of cell products. They can cause the contraction of smooth muscle or the contraction of cardiac muscle or the secretion of, actually, I'm not going to say that, never mind. So contraction of smooth muscle, contraction of cardiac muscle. This is a summary slide of a lot of the hormones we're going to talk about today. Like I told you, a lot of this is not hard to comprehend, but at the same time, it's a lot to remember. So this is a list of many, a good portion of the hormones we're going to talk about today. Their abbreviations and the organ that releases them. Casey, if you're, I know you're just connecting. Can we talk after class? Is she there yet? Not yet. We'll wait, give her a second longer. So adrenal corticotropic hormone. A lot of times you're going to learn, looking at these names, the names have a lot to do with either what they're going to do ultimately, what their target organ is, or what effect they'll have. So adrenal corticotropic hormone. If you remember the adrenal glands, this hormone has an effect on the adrenal glands. It's secreted by the anterior pituitary. ADH, antidiuretic hormone, also called vasopressin, is secreted from the posterior pituitary gland. If you can guess from the word antidiuretic, it has to do with water. Corticotropin releasing hormone is going to have an effect on the adrenal cortex. It's actually this corticotropin releasing hormone is going to stimulate the release of adrenal corticotropic hormone. You can see that from the name alone, corticotropin releasing hormone, meaning it's going to affect adrenal corticotropic hormone. Best way to learn these hormones, what I want you to understand is where they come from, what they affect. You want to learn their abbreviations. Let's see here. Bear with me here. I'm sorry. Their abbreviations, what they're called, where they come from, what their target cell is, and what their effect is. Casey, can we talk after class?
Yes.
Okay. That's what you want to remember. So do me a favor and make flashcards of these, because like I told you, there are a lot of them. The hardest part about this chapter is the fact that there's a lot of hormones. So corticotropin releasing hormone is going to come from the hypothalamus, and it's going to activate the release of adrenal corticotropic hormone. Dehydroaldosterone, whatever, or DHEA. I'm not going to try to pronounce that one. Aldosterone, I think that's how that last part is going to be released from the adrenal cortex. Erythropoietin, if you remember this one from before, erythropoietin, meaning it's going to stimulate the release of erythrocytes or synthesis of erythrocytes. Follicle stimulating hormone, anterior pituitary gland. Growth hormone, or also called somatotropin. It's going to be released from the anterior pituitary. Growth hormone releasing hormone. So meaning it's going to stimulate the release of growth hormone from the anterior pituitary. Some of them are easier than others. Gonadotropin releasing hormone is going to be involved in releasing gonadotropins. And gonadotropins are going to work on the gonads. Insulin-like growth factors going to have similar effects to that of the growth hormone. And in a lot of ways similar to insulin. Luteinizing hormone going to affect the gonads. Norepinephrine, oxytocin, prolactin inhibiting hormone or dopamine, hypothalamus. Prolactin, anterior pituitary hormone. So prolactin inhibiting hormone is going to inhibit the release of prolactin from the anterior pituitary gland. Parathyroid hormone secreted by the parathyroid glands. Triiodothyronine coming from the thyroid gland. Thyroxine coming from the thyroid gland. Thyroid hormone coming from the thyroid gland. Thyrotropin releasing hormone coming from the hypothalamus. Thyroid stimulating hormone coming from the anterior pituitary that's going to act on the thyroid gland. Another slide showing a review of the hormones coming from each of the type organs. The way hormones are classified, they have two major ways of affecting. They're hydrophilic or they're hydrophobic. So hormones are classified based on their solubilities because that's going to result in how their mechanism of action. Hormones that are hydrophilic are peptide and amino acid hormones. They can't pass through plasma membranes. So they're going to bind to the surface of the plasma membrane to a receptor. And when they bind to that receptor, they're going to activate a signaling cascade. Most often, they alter the effects of proteins that are already present. They're already transcribed and present in the cells. Hydrophobic or lipophilic proteins are transported by being in the blood or by being bound to plasma proteins. And they, because they're hydrophobic or lipophilic meaning they work well with lipids, dissolve well in lipids, are going to pass through the plasma membrane, bind to a receptor within the cell, and affect DNA expression and gene transcription protein. So they're most likely going to alter the effects or alter the numbers of proteins that are present within the cell, either by increasing the amount of proteins within the cell or decreasing the amount of proteins within the cell. Hydrophilic proteins are going to are going to affect the activities of proteins that are already present within the cell. Hydrophobic affect the numbers of proteins that are present or absent in the cell. So hydrophilic proteins alter pre-existing proteins via second messenger systems. And bind to a receptor on the surface because they can't go through the plasma membrane. And the result is that starts a signaling cascade into the cell, affecting the activities of proteins present within the cell. Most often, the signaling cascade occurs through using cyclic AMP or through calcium. Lipophilic or hydrophobic proteins, they're going to pass through the membrane, bind to a receptor within the cell, which is going to bind to the DNA, altering the gene expression, promoting the synthesis of new proteins, or preventing the expression of new proteins. Peptides and catecholamines or tyrosine derivatives are hydrophilic. Thyroid hormones and steroids are lipophilic. Peptides and catecholamines, and I know some of this is repetition, but repetition is never really a bad thing. Peptides and catecholamines are activating second messenger systems because they're hydrophilic. Lipophilic or hydrophobic proteins are activating specific genes to make new proteins that produce the effect. The majority of hormones are peptides. Catecholamines are only going to come from the adrenal medulla. Thyroid hormones only come from, shockingly, thyroid follicular cells. Steroids come from the adrenal cortex and gonads. This is a summary of those different classes and the hormones that belong to each of these classes. So steroids, examples of steroids, testosterone and estradiol. Estrogen's also classified here, just slightly different than estradiol. Monoamines, thyroxine coming from the thyroid gland. Epinephrine. Remember, epinephrine was also a neurotransmitter, so a lot of our neurotransmitters are also hormones. A lot of our hormones are neurotransmitters. It's really what their response is that classifies them as being one or the other. Peptides, oxytocin, insulin. Peptides and polypeptides, remember, they're hydrophilic, meaning they're not lipid soluble. So they're going to bind to receptors on the surface of target cells. amino acid derivatives. Most are not lipid soluble and they bind to receptors on the surface of the target cells. Steroids are always hydrophobic. They bind to receptors within the cells and alter gene expression. So when a hydrophilic hormone acts on a second messenger system, its receptor on the surface is going to activate a G protein. A G protein is going to hydrolyze GTP. Remember ATP, adenosine triphosphate. GTP is the derivative guanosine triphosphate. So it's just another nitrogen base, which a GTP is not your most common energy currency, but it is an energy currency. So GTP gets hydrolyzed to GDP, and that activated G protein through the hydrolysis of GTP activates adenylate cyclase. Adenylate cyclase produces cyclic AMP. Cyclic AMP then goes on to activate multiple protein kinases. Remember what kinases do. Kinases add phosphates to other proteins. This is important, so I'm gonna take a second really quick here. Jade, I don't need to talk to you after class unless you want to talk to me. We don't need to talk after class.
Fine, my internet just cut out, so I didn't know who you were saying in the beginning.
It's all right. So kinases are enzymes that are going to add phosphate groups. Remember, that's one of those functional groups, inorganic phosphate groups. To proteins or enzymes, other enzymes. So kinases, enzymes that add phosphate groups to other proteins or enzymes, which activates or deactivates the given protein that had the phosphate group added to it, which activates or deactivates the latter proteins. I'm going to put one more here. Phosphatases, because these do the opposite of what kinases do. Phosphatases are enzymes that remove phosphate group from proteins or enzymes. Which activates or deactivates those latter proteins. So essentially what these are is they will either, kinases will add a phosphate group, phosphatases remove those phosphate groups. When you add the phosphate groups, you can either turn on or turn off the protein's activity. The phosphatases do the opposite. So they remove the phosphate group, which is capable of turning off or turning off a protein. Depending on the protein, we're adding the phosphate will turn it on or turn it off. Removing it will turn it on or turn it off. It just depends on the protein. So these are essentially a light switch. Turning it on or turning it off. Any questions? So cyclic AMP in this case is going to activate protein kinases. Protein kinases are going to phosphorylate enzymes, meaning they're going to add that phosphate group. This is going to activate some enzymes and deactivate others. The activated enzymes catalyze the metabolic reactions within a wide range of possible effects on the cells. Another way that these hydrophilic proteins can act is they can act through what's called, let's see, inositol phosphate and diacylglycerol. So the G protein activates this phospholipase. Instead of adenylate cyclase, it's going to activate this phospholipase, which is going to cleave a phospholipid into diacylglycerol and inositol triphosphate. Diacylglycerol is going to go on and activate protein kinases that are going to activate enzymes, just like we saw before. Inositol triphosphate is actually going to act on the sarcoplasma. Remember the special calcium reservoir, sarcoplasmic reticulum, that stores calcium. It's going to activate calcium release into the cell. Remember what calcium does. It's involved in muscle contraction and protein synthesis and exocytosis of hormones. I remember how calcium works on the contraction of actin with myosin. So some hormones are going to be involved in calcium release, which goes on to have various effects. This amplification system, this is a signaling cascade, so it sometimes it takes a while to get started, but one stimulus can have multiple effects. One hormone turns on multiple adenylate cyclase enzymes. One adenylate cyclase enzyme, so one hormone, let's say, for example, one hormone activates one adenylate cyclase. Or actually, let me put it a different way, bear with me here. One hormone affects 10 adenylate cyclase enzymes. Each adenylate cyclase enzyme produces 10 cyclic AMP. So one hormone, 10 adenylate cyclase enzymes. Each adenylate cyclase and activates 10, makes 10 cyclic AMP. Each of those cyclic AMP goes on to affect another 10 protein kinases. Each of those protein kinases goes on to affect another 10 enzymes. Each of those enzymes, because enzymes can catalyze a reaction over and over again, and as soon as they finish one change, they go on and do another, they make another product. They go on to make another product. They go on to make another product. And so what you get is this reaction cascade where one hormone results in thousands of changes. I thought this another way because I felt like that my explanation there was kind of rough. So hormone cyclic AMP. Actually, I'm gonna add some more steps that wasn't there in that triangle. Adenylate cyclase. Remember what the adenylate cyclase does is it makes cyclic AMP. Adenylate cyclase makes cyclic AMP. Cyclic AMP turns on protein kinases. And each protein kinase turns on an enzyme. Each enzyme makes multiple products. So one hormone activates 10 adenylate cyclase enzymes. This is just an example. Each of those cyclase enzymes activates 10 cyclic AMP. So now we've got 100 cyclic AMP because each of those cyclases make 10 cyclic AMP. Each of those cyclic AMP activates 10 protein kinases. So now we have 1,000 protein kinases that are activated. Each of those protein kinases activates 10 enzymes. So now we have 10,000 activated enzymes. Each enzyme is capable of activating 100 making 100 products. So now we end up with 1 million products. That's what the signal amplification is all about. That one hormone can have multiple effects, and it's a signaling cascade all the way down. All of the steroids, remember the steroids are the ones that are going to alter gene expression. They're lipophilic. All steroids are derived from cholesterol. Progesterone, cortisol or hydrocortisone, aldosterone, testosterone, estradiol. They're all derivatives of cholesterol. These steroids diffuse through the plasma and nuclear membrane of their target cells and bind to a nuclear receptor, bind to a receptor for that hormone. The hormone receptor then binds to a response element on the DNA. When that hormone receptor binds to that response element, it's going to activate the expression of specific genes or deactivate the expression of other genes. So it activates the expression of genes producing messenger mRNAs. The messenger mRNA leaves the cell, and in the cytoplasm, it's made into proteins. These proteins then go on to perform enzymatic or structural effects, accomplishing whatever the response was that the hormone was supposed to result in. Questions? Hormones you secrete, and their secretion is regulated by self-adjusting feedback loops. You remember there's two types of feedback loops. You have negative feedback loops and positive feedback loops. In a negative feedback loop, the stimulus starts a process and a hormone causes the process to slow down or turn off. One example is blood glucose regulation. Eating a meal increases your blood glucose. In response to elevated blood glucose, insulin is secreted. Insulin is going to ultimately bring about a decrease in the blood glucose levels. Eating food elevates blood glucose levels. Insulin is going to be secreted. The insulin is going to cause the liver and muscle cells to take up the glucose. And that's going to bring down the blood glucose levels. And when the blood glucose levels drop below a certain level, insulin stops being secreted. Positive feedback loop. Instead of the initial signal stopping the final, we're bringing an end to the process. Positive feedback loop is going to accelerate the original process, ensuring that it continues or speeds up. A baby suckling stimulates oxytocin release. Oxytocin stimulates milk release. As the baby continues to suckle, there's more oxytocin released, causing more milk release. Once
Makes-
the baby, go ahead.
Makes you tired and thirsty. Because
I,
if anybody-
I can
if it-
imagine.
if anybody's ever nursed their baby, it's like all of a sudden you're like, oh my God, I'm tired and I'm so thirsty.
Well, and you know what? Bring that up in a couple days, Claire, because why would it make you thirsty? Going off on a tangent really quick, why would it make you thirsty?
Because it releases another hormone.
No,
Like
what do you think? Why would putting a bunch of water out for your baby / milk cause you to get thirsty?
Because you're dehydrated.
You're dehydrated. Bring this up in a couple days because we'll talk about how volume changes occur. And so, yeah, you get dehydrated. But the other thing is, what does oxytocin do? And this is just a guess on my part, the second part of what I'm going to say. What does oxytocin also do? Oxytocin causes muscle contractions.
I was going to say, isn't that the same
For the
used for labor?
Say it one more time.
Isn't it the same hormone that is used to stimulate labor?
Yes, it
Okay.
is. From what I understand, and having never had a child, I don't understand a lot of it. But when you want to get your figure back, nurse your babies. If you want to get it back to the best you can, because from what I understand, it kind of destroys your figure to have a baby. Thankfully, I haven't had one yet. Not that I'm not self-sacrificing enough for that one, but I'll leave it to you other people to have all those children. I like children. I'm just not, I've never been in the right place to be having a child.
Yep, it's too late for me.
Darn it, Casey. I'm jealous and I'm not. For someone who I sincerely like little kids. Every Sunday I take care of a bunch of 18-month-old to 3-year-olds for a little while.
Whoa.
I
That's
love
really jumping in the deep end there.
Well,
Yeah.
and I sincerely enjoy little kids. I think they're so much fun and it keeps life entertaining and it kind of gives me my kid fix.
And you get to give them back.
And then I get to give them back, right? But that's also the reason I've chosen never to be a single parent. If I have a choice of not being a single parent, I'm not going to be one.
It's
All
a
right.
lot. It
Yeah.
would be a lot.
Okay, so now I'm going to stop talking about that. Let's come back to this. So how are hormones regulated? Often they're regulated by other hormones. So one hormone regulates the secretion of a hormone from another gland. Hormones can stimulate and maintain their endocrine target tissues. Solute blood levels, blood calcium levels, blood glucose levels are going to activate hormones. The nervous system, neuronal activity, adrenaline or epinephrine from the adrenal medulla in response to conduction activation of the sympathetic nervous system. A hormone can influence the activity of another hormone through one of three ways. One hormone, it can occur through permissiveness, meaning one hormone must be present in adequate amounts for the exertion of another hormone's full effect. So if one hormone is not present, another hormone's effect is only minimal or not maximized. Synergism, when multiple hormones are complementary to one another. They each have separate effects, but their combined effects are greater than the sum of all their separate effects. Antagonism occurs when one hormone causes the loss of another hormone's receptors. One hormone causes the removal of another hormone's receptors, reducing the effectiveness of the second hormone. An example of hormonal communication, so this is talking about this up here, regulation of hormones. An example of hormonal regulation is when osmoreceptors, you guys, what are osmoreceptors? What do you think they are?
Blood?
Let's, what could be another thing, Claire? Rather than blood, what else?
Osmo?
Yep.
I'm the word for in medical terminology is not coming to me.
Osmolarity.
Isn't it? Yeah.
What about osmosis? What's osmosis? Someone tell me by definition, what is osmosis?
Is like a gradient from below. Pressure gradient.
A pressure gradient that does what?
Diffusion.
Diffuses.
Diffusion of what, Martin? Or Claire?
Blood pressure.
Yep. And what's the majority of blood pressure being caused by?
I'm sorry, can you repeat that?
What's the majority of blood pressure being caused by? What causes blood pressure?
ADH.
We're all circulating around the word. How about water pressure? Hydrostatic pressure. So osmoreceptors, this was a question that actually came up in my physiology class yesterday. Osmoreceptors, what are they sensing? They're sensing water concentrations. So an example of hormonal communication is when osmoreceptors blank of the blank detect dehydration. A signal then goes to the posterior pituitary gland, causing the release of what? And I'm gonna shrink in the screen here just a sec. From last semester, where do you sense that you're thirsty?
Is it D, renin?
Hyper.
Nope, it's not. You're close though, but it's not that.
A.
Why do you say it's A, Rachel?
Well, earlier in the lecture, you told us that the hypothalamus was the major control system or center of the endocrine system. So figured that. And then the ADH is anti-diuretic. So you would retain fluid.
Retain
Right.
water, right, exactly. So that's the right answer. Good job, Rachel. So as an example of hormonal regulation, when osmoreceptors in the hypothalamus, that's where your thirst center is, where all of a sudden you get thirsty, detect dehydration. A signal to the posterior pituitary gland causes the release of antidiuretic hormone. The responsive of any target cell to a hormone can be varied by regulating the number of receptors. Remember that if the receptor isn't there, the cell doesn't respond to that hormone. So if you alter the amount of hormones, you're going to alter the number of receptors, you're going to alter the intensity of how that target cell responds to that hormone. So downregulation, when the number of receptors decreases in response to rising hormone levels, the cellular activity gets reduced, preventing the target cells from overreacting to a prolonged high concentration. And I know we take a break about right now, but I am not going to take one because I've got to get through the endocrine system today. And I'm sorry I had internet issues initially, but we've got to finish this today. So I'm not going to take a break right now like we normally would. It prevents the target cells from overreacting to a prolonged high concentration of their hormone. Upregulation, where the number of receptors increases in response to rising hormonal levels, making the cell more sensitive to the hormone, allowing for more cellular activity. So upregulation, you start with a low receptor density. The hormone comes in and starts binding to the receptor. And as a result, you get increased receptor density, resulting in a stronger response. Because the more receptors that get activated, the more cascades you have. Downregulation, a high receptor density, a strong response. Reduced receptor density, reduced sensitivity. Because if the less receptors you have, the less likely you are to have a response. Something that needs to be brought up, nervous system control of hormones and adaptation. Remember how the nervous system is involved in controlling hormones. Adaptation syndrome, or general, a lot of times you call this general adaptation syndrome, GAS, G-A-S. where the nervous system is going to impact hormone levels. So initially, you get epinephrine and norepinephrine being released. The heart rate increases. Blood pressure increases. Bronchioles dilate. This is when you see the bear in front of you. You guys, if you remember this from last semester, this is your fight or flight response. This is sympathetic nervous system activity. The liver immediately starts converting glycogen to glucose and releases glucose to the blood. The blood flow changes, reducing digestive system activity and urine output while increasing muscle metabolic rates. Long-term stress responses, rather than being able to get away from the bear, now you're dealing with long-term stress, like a major injury or a death of a member of your family that you're close to. Kidneys will retain sodium and water. Blood volume and blood pressure rise. Proteins and fats are converted to glucose or broken down for energy. Blood glucose increases. The immune system is suppressed. I'm going to pause just for a second here. There's 3 stages here. One, I have to remember, let's see here. I think it's called the alert stage. Sympathetic nervous system activation. All of a sudden your epinephrine levels are going up. Your fight or flight mechanism is getting turned on. Next one is your resistance stage. Getting cortisol being released to help with your increased stress levels. Resistance stage. So adrenal glucocorticoids are getting elevated that are from the adrenal glands. Glucocorticoids. Glucocorticoids. Three, exhaustion stage, where your stress levels are becoming debilitating.
Don't we all function that way?
Oh, well, you function that way, Claire. Hopefully not everyone functions that way all the time. Exhaustion stage, meaning that your immune system is depressed because your cortisol levels have been high for way too long. Cortisol temporarily suppresses your immune system. However, when it goes on for too long, it's now detrimental. And so during this resistance stage, you started burning up your fat storages to develop energy. In the exhaustion stage, rather than just develop, now your fat storages are gone and all you have left is muscle. You start breaking down your muscles, and this is catabolic. Not that breaking down your fat wasn't catabolic, they both are. But now rather than you've run out of your fat storages and now you're running through your muscles and destroying your muscles. So hopefully we're not all living like that, Claire. That's bad.
I was in the exhaustion stage over spring break. I was sick.
Ah,
My body finally was like, enough is enough.
ouch.
Yeah, it was not how I wanted to spend my spring break, but oh well.
So this is destroying, going through your fat storages. Are
I'd be skinnier if that were true.
but you know what? The other thing that it does is it starts messing with your body. That's why a lot of women who are anemic are also severely overweight, and it's not always women.
I also have HPV like related vulvar cancer,
Ouch.
which is like it's non-metastatic and anyway, but it's immune responsive. So
Isn't that human papilloma virus, Claire?
yeah, I mean, I don't have
Ouch.
like my doctor's like anybody who's ever been sexually active has HPV.
Oh,
but
really? I didn't know
yeah,
that.
that's what she told me. But anyway, I had like a little like skin cancer removed. I mean, it
Yeah.
wasn't a little surgery. I was put like under to
Wow.
have it. But it's immune responsive. So like, even though like the piece of cancer was gone, like they removed it, like it can come back based on my immune system.
Oh, wow. Okay.
Sadly.
So this would be your first stage, your alert stage. This is your resistance stage. This is your exhaustion stage. Actually, that's not completely correct. Just remember there's 3 stages. Because your immune system gets suppressed during the resistance stage. It's not overly suppressed. Questions? So hypothalamic control of the endocrine system. The hypothalamus is the master controller and the center of the endocrine system. It's located in the inferior region of the diencephalon, just superior to the pituitary gland. It controls the release of regulatory hormones from the anterior pituitary and is going to secrete oxytocin and antidiuretic hormone from the posterior pituitary gland. It also controls the stimulation and secretion of activities from the adrenal medulla. The reason we call it the master controller. The pituitary gland is also called the hypophysis. It's located just inferior to the hypothalamus, and it's housed within the sella turcica of the skull plate of the sphenoid bone. It's connected to the hypothalamus. The pituitary gland is connected to the hypothalamus via a thin stalk called the infundibulum. And the gland is divided into the anterior lobe, the adenohypophysis, and the posterior lobe, which is the neurohypophysis. Talk about why we call one the adeno, one the neuro in 1 second here. So here, the anterior lobe, the posterior lobe, the infundibulum, the hypothalamus. hypothalamus produces releasing hormones and inhibiting hormones that are directly going to affect the anterior pituitary hormone secretion. The hypothalamus also produces two hormones itself that are stored in the posterior pituitary gland: oxytocin and antidiuretic hormone. It also oversees the autonomic nervous system by stimulating the adrenal medulla via sympathetic innervation. So hypothalamus, infundibulum, anterior pituitary or adrenal hypophysis, posterior pituitary or neural hypophysis. Hormones that are coming from the hypothalamus: gonadotropin releasing hormone, thyrotropin releasing hormone, so gonadotropin, just to help with thinking about what these things are doing, long names, but gonadotropin, what does that have to do? It has to do with the gonads. Ultimately, that's what it's going to affect. Thyrotropin ultimately is going to affect the thymus and the thyroid gland. Corticotropin, the adrenal cortex. Prolactin, lactation, the mammary glands. Growth hormone, the thyroid gland. Somatostatin, that works in opposition to the growth hormone. Also keep in mind that the hypothalamus is going to produce the two hormones, oxytocin and antidiuretic hormone, that are going to be made in the hypothalamus but stored in the posterior pituitary gland. So anterior lobe hormones, follicle stimulating hormone, and luteinizing hormone are both going to affect the gonads. Thyroid stimulating hormone, shockingly, it affects the thyroid gland. Adrenal corticotropic, working on the adrenal cortex. Prolactin, growth hormone. So thyrotropin releasing hormone is going to affect prolactin releasing hormone and thyroid stimulating hormone. Gonadotropin releasing hormone is going to affect luteinizing hormone and follicle stimulating hormone. Corticotropin releasing hormone is going to affect adrenal corticotropic thyroid hormone. Actually, let me say that again. Adrenal corticotropin hormone. Growth hormone releasing hormone, shockingly, is going to cause release of growth hormone. which is going to stimulate lots of different things, including insulin-like growth factor from the liver. So insulin-like growth hormone and growth hormone have very similar synergistic acts. So just a little bit, a little bit of a review here. This is a lot of information, so I don't have, I think repetition is a good idea here. Neurosecretory cells in the hypothalamus are going to produce release and inhibiting and releasing and release inhibiting hormones. Other neurosecretory cells are going to produce antidiuretic hormone and oxytocin. Antidiuretic hormone and oxytocin are going to travel down axons into and be stored in the posterior pituitary. When appropriate, antidiuretic hormone and oxytocin are going to be secreted from axon endings in the bloodstream. The anterior pituitary is going to secrete its hormones into the bloodstream. Gonadotropins, growth hormone, prolactin, adrenocorticotropin hormone, and thyroid stimulating hormone. Looking at the anterior pituitary, it has three basic types of cells. It has chromophobes, acetophils, and basophils. Looking at the posterior pituitary, the one way that you can definitely tell the histology of the anterior pituitary from posterior pituitary is the posterior pituitary has a lot of axons in it. Because remember, that's how antidiuretic hormone and oxytocin are being stored and into the posterior pituitary. So a lot of what you're seeing when you're looking at the posterior pituitary is a lot of myelinated axons. In the anterior pituitary, the acetophils are going to produce growth hormone and prolactin. The basophils are going to produce thyroid stimulating hormone, adrenocorticotropin hormone, follicle stimulating hormone, and luteinizing hormone. This is a list, and you're going to see these throughout because I told you this is a major part of this chapter is memorizing where these hormones are coming from, what their names are, and what their effects are. Hormones released from the hypothalamus. Thyrotropin releasing hormone promotes the secretion of thyroid stimulating hormone and prolactin from the anterior pituitary. Corticotropin releasing hormone promotes the secretion of adrenocorticotropic hormone from the anterior pituitary. Gonadotropin releasing hormone is going to promote the secretion of follicle stimulating hormone and luteinizing hormone from the gonad, from the anterior pituitary. It's going to affect the gonads. Growth hormone releasing hormone promotes the secretion of growth hormone. Prolactin inhibiting hormone is going to inhibit the secretion of prolactin. from the mammary glands. And secrete is going to block the secretion of prolactin, which is that acts on the mammary glands. Somatostatin is going to work as an antagonist to growth hormone, inhibiting the secretion of growth hormone and thyroid stimulating hormone. This is showing the way that oxytocin and vasopressin are released. Vasopressin, antidiuretic hormone, another name for antidiuretic hormone, vasopressin, is going to act on the nephrons in the kidneys and the arterioles throughout the body. Oxytocin is going to act on the uterus and the mammary glands. So 2 clusters of neuronal secretory cells in the hypothalamus produce vasopressin or oxytocin, and the hormone travels down the axon to be stored in neuronal terminals within the posterior pituitary. When the neuron gets excited, the stored hormone is released from the terminals into the systemic blood for distribution. So hormones originating from the pituitary gland. Follicle stimulating hormone is going to target the ovaries and the testes. It's going to, in females, it's going to result in growth of the ovarian follicles and secretion of estrogen. And in males, sperm production. Luteinizing hormone is going to, in females, is going to cause ovulation and maintenance of the corpus luteum, which is going to secrete progesterone. In males, luteinizing hormone is going to cause testosterone secretion. Thyroid stimulating hormone is going to target the thyroid gland, growth of the thyroid, and secretion of thyroid hormone. Adrenal corticotropin hormone is going to target the adrenal cortex and cause growth of the adrenal cortex and secretion of glucocorticoids. Prolactin is going to target the mammary glands, resulting in milk synthesis. And oxytocin is going to cause milk letdown. So they're going to work in conjunction with one another. Growth hormone affects multiple tissues, liver, bone, cartilage, muscle, and fat, causing widespread tissue growth, especially in the stated tissues. Antidiuretic hormone is going to affect the kidneys, causing water retention. Oxytocin is going to target the uterus and mammary glands, causing labor contractions, milk release, possibly involved in ejaculation in males, sperm transport, sexual affection, and mother-infant bonding. Which hormone stimulates glucocorticoid secretion? Guys, it's going to be, just to save time here, it's going to be the adrenal corticotropic hormone, because that it's affecting the adrenal cortex, which is what's secreting glucocorticoids.
So what'd you say it was?
It's going to be the adrenal corticotropin hormone.
Thank
If it helps, think of glucocorticoids. They're coming from the adrenal cortex. Cortico meaning the adrenal cortex. That's how you can remember that this is what's going to cause the secretion. Adrenal corticotropin is going to cause glucocorticoid secretion. Which of these hormones does not stimulate the release of another hormone by its targeting cells? And now I have to remember, I've got to remember from the other night, which of these hormones does not stimulate the release of another hormone by its target cells? I think it's PRL.
What is that one? What's PRL?
I knew you were going to ask me that. Bear with me. I'm going to come up and look. Because I honestly, I'm not even sure if it's a hormone. I think that's a trick question. Prolactin. It causes milk synthesis, but it doesn't cause another hormone to be released from the mammary glands.
Got it. Thank you.
Okay. Blank secretes growth hormone, also known as somatotropin. This is the anterior pituitary. Is going to secrete growth hormone, also called somatotropin. Remember, somatostatin is released from the hypothalamus, and it inhibits the effects of growth hormone or prevents its secretion. The anterior pituitary blank is blank and has connection to the hypothalamus. First off, the anterior pituitary has no neuronal connection. So when we're looking at this, it has no neuronal connection. And now I have to remember, bear with me here. I think it's similar in size to and has no neuronal connection to the hypothalamus. This is one that we didn't really cover before, but diabetes insipidus. What this means, it's not glucose related. It makes you think that it's glucose related because one of the symptoms is very similar to when you first start developing type 1 diabetes. But diabetes insipidus is caused by hyposecretion of antidiuretic hormone from the posterior pituitary. And the result is that you do not reabsorb water very well from your kidneys. And as a result, they're constantly thirsty. Even though you can't, your blood volume is dropping. And therefore your thirst center in your hypothalamus is being activated. But you're not reabsorbing the water. And so it just keeps going. You're always thirsty, but you're not reabsorbing the water that would quench your thirst and allow you to maintain your blood volume. So it's antidiuretic hormone hyposecretion. D is in delta. The adrenal cortex. You guys, do you have any questions for me? Like I said, I don't want to take a break because I really want to work through. We're a little behind and I want to finish the endocrine system. So be patient with me here. The adrenal gland has two main parts, the cortex and the medulla. The cortex has three layers, the zona glomerulosa, the zona fasciculata, and the zona reticularis. Each of these three layers is going to secrete different hormones. So the cortex, the adrenal, which is made of the zona glomerulosa, the zona fasciculata, the zona reticularis. And then the adrenal medulla. The zona glomerulosa, most inner layer, actually most outer layer of the cortex, is going to secrete mineral corticoids, specifically aldosterone. Aldosterone is going to target the kidney tubules to reabsorb sodium. Aldosterone is released when there's too much potassium or when it's stimulated by another hormone called angiotensin II. Zona fasciculata is going to secrete the glucocorticoids, cortisone and hydrocortisone. It's going to allow the body to resist long-term stressors and reduce the immune response. These glucocorticoids are released in response to the anterior pituitary releasing adrenocorticotropin hormone. The zona reticularis is going to secrete androgens or gonadocorticoids. And they're partially released in response to adrenocorticotropin hormone. The adrenal medulla is going to create adrenaline. which is a mixture of epinephrine and norepinephrine. Sympathetic nervous system is going to result in these being released. Adrenaline is going to target many cells in the body and produce the fight or flight response of the stressors. So the hormones that are coming from the adrenal gland. In the adrenal medulla, epinephrine, norepinephrine, and some dopamine. Targets most tissues, promotes alertness, mobilizes organic fuels, raises metabolic rate, stimulates circulation and respiration, increases blood glucose levels, inhibits insulin secretion and glucose uptake. Adrenal cortex secretes aldosterone, that first layer, the zona glomerulosa. Aldosterone, which promotes sodium and water retention and potassium excretion. Cortisol and corticosterone is going to stimulate fat and protein catabolism, gluconeogenesis, remember that's producing new glucose, stress resistance, and tissue repair. DHEA, we're just going to call it that from here on out, DHEA is a precursor for testosterone. It's going to indirectly promote the growth of bones, pubic and axillary hair, apocrine glands, fetal male reproductive tract, and stimulates libido. A patient displays symptoms of excessive cortisol secretion. So there's something that's causing them to secrete a lot of cortisol, which is coming from the adrenal cortex. What factors could be measured in a sample to determine whether the condition is caused by a defect of the hypothalamus, anterior pituitary level, or the adrenal cortex level? Well, I would look to see if their corticotropin releasing hormone levels are down. Or if their adrenal corticotropin hormones are down. If those amounts are excessive, that means that the receptor that should be stopping cortisol release is not working. So when these two are building up, but we still are producing a lot of cortisol, or we're not producing enough, actually, bear with me here. Back up, Mary. Excess cortisol. They're producing a lot of cortisol. The reason they would be producing a lot of cortisol is if we either have a lot of corticotropin releasing hormone or a lot of adrenal corticotropin hormone. And if you would want to measure the levels of these two hormones and determine if they're normal or if they're low. Questions? Thyroid or parathyroid glands. The thyroid glands around the thyroid cartilage contains follicles and follicular cells. Within the follicles is stored thyroglobulin. The parathyroid hormones, parathyroid glands are going to produce parathyroid hormone. Which is going to affect calcium levels. And stimulate blood calcium levels. Another hormone that comes from the thyroid gland is calcitonin, which has an inhibitory effect on parathyroid hormone. So cells of the thyroid gland, the principal cells or the follicle cells, are going to respond to thyroid stimulating hormone from the anterior pituitary gland and make thyronine or thyroxine, T3 and T4. T3 and T4 are going to target many body cells regulating metabolism. Another thing that we call T3 and T4 is thyroid hormone. Parafollicular cells, in contrast, are going to release calcitonin, which is going to decrease blood calcium levels by stimulating osteoblasts. Remember, calcitonin works in opposition to parathyroid hormone. So how is thyroid hormone produced? One thing that we really need to produce, that's a major requirement for thyroid hormone to be produced, is iodine. This is the reason that a lot of the salt that we eat is iodized, is to allow us to get our iodine, because that's the only way you get it is through your diet. Iodide is oxidized and combined in the principal cells with thyroglobulin. Thyroglobulin can either have one iodine attached to it or two iodine molecules attached to it. Then it's stored as this iodized thyroglobulin molecule. These monoiodized thyroxine and diiodized thyroxine will combine together. One monoiodized thyroxine to one diiodized thyroxine is going to produce T3, because there's going to be three iodines molecules. 1, 2, 3. 1, 2, 3. If two iodized thyroxine molecules combine, they are going to form a tetra iodized molecule, T4. That's a major difference between T3 and T4. One is one monoiodized thyroxine molecule, and one diiodized thyroxine molecule. T4 is 2 diiodized thyroxine molecules combined. And these T3 and T4 are both thyroglobulin molecules. Like most hormones, the release of thyroid hormone is going to be regulated by a negative feedback loop. Thyrotropin releasing hormone is going to come from the hypothalamus and act on the anterior pituitary. Releasing, which is going to result in the release of thyroid stimulating hormone, which is going to cause the release of thyroid hormone that goes out and affects all its target organs. The increased amounts of thyroid hormone in the blood are going to inhibit thyroid stimulating hormone secretion and thyroid hormone releasing hormone secretion. So it cycles back, causing this negative feedback loop. So the release of thyroid hormone inhibits its own production by acting on the hypothalamus and the anterior pituitary. If you feel like your head's going to fall off right now, that's normal because there's a lot of information here. Would you expect the concentration of thyroid stimulating hormone to be normal, above normal, or below normal if a person's diet is deficient in iodine? Guys, if you're not producing enough iodine, you're not going to produce enough thyroid hormone. If you don't have enough iodine, you don't have enough thyroid hormone. It's going to be above normal because you're not going to be producing enough thyroid hormone. If your diet's deficient in iodine, so you're not producing enough thyroid hormone, your body is going to keep putting out thyroid stimulating hormone to see if it can't bump up the thyroid hormone levels, even though it's doing its job. You still don't have enough iodine to make thyroid hormone. Does that make sense? Because your diet is deficient in iodine, you can't make enough thyroid hormone. But because you're not producing enough thyroid hormone, your pituitary gland is going to keep producing thyroid stimulating hormone to see if it can't bump up your thyroid hormone levels. It doesn't understand that you're deficient in iodine. It just knows you're not producing enough thyroid hormone. And the result is that it keeps producing thyroid stimulating hormone. So the hypothalamus is going to act on the thyrotropin releasing hormone. It's going to secrete thyrotropin releasing hormone, which is going to cause the release of thyroid stimulating hormone from the anterior pituitary gland, which is going to cause the increase of T3 and T4 from the thyroid gland. So it's going to cause increased metabolism because, and the amounts of thyroid hormones are going to negatively have a negative feedback loop and inhibit thyrotropin releasing hormone secretion and thyroid stimulating hormone secretion. Thyroid hormone also is involved in regulating your temperature. Hotter temperatures cause the hypothalamus to inhibit thyroxine release from the thyroid by reducing the amount of thyrotropin releasing hormone, decreasing the metabolic rate of the body to reduce heat production. Colder temperatures are going to cause the hypothalamus to release more thyrotropin releasing hormone, which is going to act on the anterior pituitary gland to result in increased thyroid stimulating hormone, which is going to cause more thyroid hormone to be produced, increasing the metabolic rate of the body and to generate body heat. Two types of cells in the thyroid gland. Chief cells make up produce the thyroid hormone in the thyroid gland. What oxyphil cells make in the parathyroid gland is unclear. Parathyroid hormone is released when blood calcium levels are too low. Parathyroid hormone then targets the bone, stimulating osteoclasts to break down the bone, releasing more calcium into the blood. It also works on the kidneys to cause calcium reabsorption, and works on the small intestines to absorb calcium from our food, us to absorb more calcium from our food by activating vitamin D. So when blood calcium levels are low, parathyroid glands release parathyroid hormone that causes blood calcium levels to rise. When blood calcium levels are too high, the thyroid gland is going to release calcitonin, which is going to activate osteoblasts, bringing down blood calcium levels. Which cell in the parathyroid hormone secretes, and which cell in the parathyroid gland secretes parathyroid hormone? It's the chief cells. And up here, it's the chief cells. Pineal gland, remember, it secretes melatonin that's involved in maintaining the 24-hour circadian cycle and sexual maturation. The thymus gland secretes 3 different hormones that are involved in regulating and maintaining the body's immunity. Remember, the thymus gland is the training ground for the T cells of the immune system. So hormones originating from the pineal gland, thymus, thyroid, and parathyroid glands. Pineal glands, melatonin acts on the brain. Thymus secretes thymopoietin, thymosin, and thymulin. Stimulating T lymphocyte development and activity. The thyroid gland acts on the thyroxine. Excuse me, thyroid gland produces thyroxine and triiodine thyrene that work to elevate metabolic rate, heat production, increase respiratory rate, heart rate, strength of heartbeat, stimulate appetite and accelerate the breakdown of nutrients, promote alertness and quicken reflexes, stimulating growth hormone secretion and the growth of skin, hair, nails, teeth, and fetal nervous system development. Excuse me. Calcitonin, produced by the thyroid gland, targets the bones, stimulates bone deposition, mainly in children. Parathyroid glands produce parathyroid hormone that targets bone, kidneys, and small intestines and works to raise blood calcium levels. Pancreas. You guys, do you have any questions so far? So like I said, make flashcards of these. The pancreas has both exocrine and endocrine functions. There's two types of cells, pancreatic acini and pancreatic islets. Pancreatic acini are going to have digestive functions. They produce gastric juices and digestive enzymes. Pancreatic islets are going to secrete insulin and glucagon. The pancreatic islets are going to have alpha cells and beta cells. Alpha cells secrete glucagon. Glucagon is released when the pancreatic glucose levels are too low. It's going to stimulate the liver to break down the stores of glycogen and make new glucose. Beta cells secrete insulin, which it's going to be released when blood glucose levels are too high, stimulating the cells to take up the blood glucose out of the blood. So islets are distinguished from the exocrine pancreatic acini cells because of their connective tissue capsule. The glucagon alpha cells stain red. You see that here? We'll zoom in a little bit. So the alpha cells stain red, while the beta cells stain blue. Remember, the alpha cells secrete glucagon, the beta cells secrete insulin. Hormones that originate from the pancreas. Pancreatic islets are where they're all going to come from. Glucagon, insulin, somatostatin, and gastrin. Main ones that we talked about, glucagon and insulin. Glucagon is going to work to elevate blood glucose levels. Insulin is going to work to reduce blood glucose levels. Which of the following is true about the pancreas? Let me come back and This is where it is. Here's the duodenum. Stomach would be about right here. And the spleen would be about right here.
B.
B is in Bravo.
Yes.
Yes. Which of the following is not secreted by the pancreas? It's somatotropin growth hormone. So insulin insulin facilitates glucose transport into cells. So it works to bring glucose into cells. It stimulates glycogen. Remember that glycogen is the storage molecule of glucose in skeletal muscle and liver. It inhibits glycogenolysis, breaking down glycogen, because you're trying to build up glycogen, not break it down. It's going to inhibit making more glucose, gluconeogenesis. It's going to inhibit lipolysis, breaking down lipids, because we want to use glucose. We don't want to use lipids for energy. Glucagon is going to increase hepatic glucose production because it's going to work to elevate blood glucose levels. It's going to enhance ketone production. It's going to promote lipolysis and inhibit triglyceride production. And it's going to inhibit hepatic protein synthesis. All of these things, the ultimate goal of glucagon is to increase blood glucose levels. And each of these things in their own way, each of these processes in their own way is going to result in increasing blood glucose levels. Same thing, similarly here, insulin is going to work to remove glucose from the blood. Each of these in their own way is going to facilitate that process or work to prevent blood glucose levels from continuing to go up. Ovaries and testes. You guys, I'm going to go until 10:40. We will finish this at the beginning of lab because I really do want to finish the endocrine system. We will finish, we'll continue until 10:40, and then we will finish this at the beginning of lab before we start the lab. Ovaries and testes. Granulosa cells in the ovaries are going to be the source of estrogen. In the testes, the interstitial cells, or they're also called Leydig cells, which we'll see on another slide, produce testosterone. These are both acting in response. Granulosa cells and Leydig interstitial cells are acting in response to follicle stimulating hormone and luteinizing hormone that's coming from the hypothalamus and the anterior pituitary. Just a general idea of what we're looking at in the ovaries. Granulosa cells, remember they're the ones producing estrogen. Primary follicles, primordial follicles. The major one we're going to worry about right now is the granulosa cells. Ovarian hormones. Primordial follicles begin to mature. They're what's going to form your eggs, your ovum. Primordial follicles begin to mature when they start responding to follicle stimulating hormone. Think of follicle as being what's going to produce a baby. If you think of it that way, you'll always remember what follicle is, because think of a follicle as being a baby or a fetus. So primordial or primary follicle begins to mature in response to follicle stimulating hormone. Follicle cells secrete estrogen. Estrogen is responsible for secondary sex characteristics and acts with progesterone to cause the cyclic changes in the uterine lining. So primordial follicles start to form in response to follicle stimulating hormone. As they're forming, they secrete estrogen. Once the egg is ovulated from the ovary, the release of the secondary oocyte is going to be triggered by a luteinizing hormone surge. And what's left of that oocyte after it's released from the ovary, it's the shell that it's released from, becomes what's called the corpus luteum, which secretes progesterone. Guys, we will talk about the reproduction system. It's going to be the last thing we talk about, so we'll go through it fairly quickly, but this will make more sense than two. So the corpus luteum is going to secrete progesterone, which helps maintain the uterine lining. Right now, just remember what hormones are being produced from what. Testicular hormones. Inside the testes are seminiferous tubules. The sperm are produced in seminiferous tubules. Outside of the seminiferous tubules, the interstitial cells are going to produce testosterone. So seminiferous tubules are going to respond to follicle stimulating hormone. Remember that it's coming from the anterior pituitary. And they're going to produce sperm in response. Leydig cells or interstitial cells are responding to luteinizing hormone and producing testosterone. The testosterone targets multiple body cells and produces the secondary sex characteristics and sex drive. So the different hormones coming from the ovaries, and testes. Estradiol affects many tissues. It's going to stimulate female reproductive development and adolescent growth, regulating the menstrual cycle and pregnancy, and preparing the mammary glands for lactation. Ovaries are going to release progesterone, which is going to regulate the menstrual cycle and pregnancy and prepare the mammary glands for lactation. Inhibin is going to inhibit follicle stimulating secretion. In the testes, testosterone is going to stimulate fetal and adolescent reproductive development, musculoskeletal growth, sperm production, and libido. It's also going to result in inhibin being secreted. The testes is also going to secrete inhibin, which is also going to stimulate follicle stimulating secretion. Remember that follicle stimulating, think follicle as being something that has to do with a fetus. So this is going to be involved in egg development in females and sperm development in males. The placenta in females also produces estrogen and progesterone, which stimulates fetal development and maternal bodily functions and adaptations to pregnancy, and prepares the glands for lactation. So you guys, it will take us just a few minutes to finish this afternoon, and then we'll start into lab. And I have 2 kidneys. So I told you that I got some fixed kidneys, and then I got some kidneys from a butcher here in East Berlin. I don't know, because I've never dissected an unfixed kidney. We'll have to see what it's like and what we see. It's not going to probably be as interesting as the lungs were, or the heart. But let's just see what we'll go in, and we'll see what we see. But I will see you at noon.
Sounds good. Thank you.
Martin, if you're still here, just know that I'm just going to extend those things for you. I just didn't get a chance to respond to you last night. Safa, Jesse,
Yeah.
Catherine,
Yeah.
do you have questions for me?
Yes, for 25, I think 25 Wiley, I miss it.
Can
So
you,
if you can,
Safa, can you send me an email? Did you already send me an email?
I sent you a message like last week.
I thought I extended it for you already. Did I not?
No, you didn't.
All right.
Yes, I finished everything except that. So
Okay, give me 1 second.
sure, thank you.
When do you think, Safa, when do you think you can have it done?
I hope maybe Monday or Tuesday like that.
Okay, let me give you until Wednesday.
Thank you so much.
Of course, give me a second here.
Mhm. Yeah, for study case, I didn't finish it yet.
Say it
So
again.
I'm just start study case.
The case study, just
Okay,
submit it
that's
when
fine, yeah.
you're ready.
Okay, I'm just started yesterday because like,
Okay. One second here. Endocrine. That's not it.
yeah.
25. Endocrine system on structure. Or all right, let's see here. Oh. Wow, give me a second. Yeah, I didn't do it. I thought I had. Okay. Okay, Safa, I apologize for that. It's done now.
No, I apologize because I'm always have problems.
Well, you know, and it's all right. It's an online class and I understand completely. So don't worry about it.
Thank you so much. I appreciate that.
Of
Thanks.
course. Zena or Catherine, are you here?
Yeah, I'm here.
What's up? Zena? Zena, do you have a question for me? Or Catherine, do you have a question for me? Zena? Do you have questions for me? All right.
I tried.
Zena, I honestly can barely hear
yeah,
you.
can
Can you
hear
call me on
me?
the phone?
Can you hear me?
Not very well. Can you call me on the phone?
Yeah, can you hear
Not, you're cutting in and out really bad.
me? Hello?
Hi, now you're better. Safa?
Yeah, thank you so much. I'm gonna leave now.
Okay, all right.
Thanks.
No,
yeah,
it's
I
all
will see
right.
you
No
later.
worries. No worries.
No, thank you so much. I know. I
Don't
thank you
worry
so much. You
about
make
it.
the life easy. Thanks. Thank you so
You're
much.
welcome. Of course.
See
Bye-bye.
you later.
Catherine, are you here? Catherine? Okay, I'm going to end the meeting.